Hey, what's up, chemistry people? It is Mr. Boylan, and today we start our new unit on electrochemistry. We're going to start off by identifying redox reactions and justifying the identification in terms of electron transfer. Get excited, oxidation, reduction, transferring electrons. Woo! So let's break that down a little bit. As we think about redox reactions, we're going to have to be able to look at any element in a chemical reaction and determine its oxidation state. And that's going to be very useful for helping us figure out what's being oxidized and what is being reduced. Next, you're going to be able to identify the species or the thing that is being oxidized or being reduced in the redox reaction. Remember, those two things happen simultaneously. You can't have one without the other. And then lastly, you're going to balance a redox reaction using the half reaction method in either acidic or basic solutions. So those are the big three things we're going to be doing today. First, some quick notes. I would like to introduce you to my good friend Leo and what he says. Grr. Keep Leo in the back of your mind as we work throughout this entire unit, as he's going to be very, very helpful. First, when we talk about redox reactions, we're really focused on what's going on with the movement of the electrons as the reaction proceeds. And all redox reactions involve a transfer of electrons. Couple of quick terms here. If a substance in the reaction gains an electron, it is said to be reduced. Grr. If a substance loses an electron, it is said to be oxidized. That's where our good friend Leo comes into play. And it's important to recognize that in a redox reaction, electrons are transferred from the species that is oxidized, the thing that loses electrons, to the species that is reduced, the thing that gains electrons. So here's a fantastic animation that essentially shows you what happens in a redox reaction in terms of the transfer of electrons. In this reaction, we start out with iron and molecular oxygen. As we have these two things react with one another, the electrons from the iron are transferred to the oxygen. In other words, the iron loses electrons and it is oxidized, and oxygen gains electrons and it is reduced. It's important to recognize that even when you don't have strictly ionic compounds in your reaction, you can still have a redox reaction take place. So as you think about a reaction between hydrogen and fluorine to form hydrogen fluoride gas, we've got the atoms of fluorine, which are far more electronegative than the hydrogen atoms are, and they sort of pull the electrons towards them more than the hydrogen atoms do. So although we don't have a true transfer of electrons as we do in the formation of ionic compounds, you can still have sort of a movement of electrons, and that's why it's so important to write those oxidation states, because it sort of helps us keep track of what's going on with electrons, even if they're not completely transferred like we see in the formation of ionic compounds. Okay, now a couple of quick terms here to really confuse you. Reducing agent is the thing that reduces something else. So if it is reducing something else, it itself is becoming oxidized. The reducing agent loses electrons. So again, reducing agent is itself being oxidized. And then likewise, the oxidizing agent is the thing that causes something else to be oxidized, but it itself is reduced. So a couple of terms here that can be slightly confusing. It's no longer required to know these terms necessarily for the AP exam. However, they're probably going to come up, and it's going to help you in your understanding of redox reactions overall. And then lastly here, as you think about trying to understand what things are gaining electrons, what things are losing electrons, in many cases it's easiest to write what's called the net ionic equation to help us better understand and better see what things are gaining and what things are losing electrons. So you're given a quick example there in your notes, and here it's pretty easy to see that the silver ion accepts electrons from copper, and therefore we would say is reduced because it's gaining electrons. but it itself is the oxidizing agent because it causes something else, in this case copper, to be oxidized. So copper donates an electron to the silver ion and is oxidized. So copper itself is oxidized, loses an electron, but copper is considered the reducing agent because it causes the silver ion to be reduced. So just some things to sort of wrap your mind around. Again, the net ionic reaction really helps you, I think, better see what thing is getting reduced, what thing is getting oxidized, and therefore you can better determine what the reducing and oxidizing agents are. Here's our good friend again, Leo, and what does he say? That's right, he says grr. I'm just going to run through the steps really quick for balancing redox reactions, so you've got them in your notes. And then I want you to refer back to these as we are practicing balancing redox reaction using the half reaction method. Step 1, write the half reactions. So when you're given the reaction, you're going to want to split it up into the oxidation half reaction and the reduction half reaction. Step 2, first balance atoms other than oxygen and hydrogen for each half reaction. You'll do that very similarly to how you balance chemical equations using just inspection. So step 3 may sound a little tricky right now, but just bear with me. Let's get the notes down, then we'll look at some examples. When you want to balance the H and the O, basically you're going to balance the hydrogen with hydrogen ions because you're in acidic solution. You got a bunch of those free hydrogen ions just sort of floating around. And then to balance the oxygen, you'll add water. And again, we'll take a look at some examples to sort of help this make a little more sense. But in acidic solutions, you'll balance the H with the hydrogen ions, the oxygen with the water molecules. Basic conditions, you are actually going to do the exact same thing you do with acidic conditions. You're going to balance H with the hydrogen ion. You're going to use water to balance the O's. But then, as you'll see, we're going to add a little extra step here because in basic conditions, we've got a bunch of hydroxide ions, not all those H ions in solution. And we'll use those to sort of cancel out, neutralize all of the hydrogen ions. And you'll see how that sort of creates a basic solution or basic condition for us. Step 4, you have to balance the charge for each half reaction. So again, as we look at these redox reactions and the half reactions, one of the reactions is going to show the loss of electrons, the other is going to show the gain of electrons, and it's important that you have a balanced charge in addition to a balanced mass. Step 5, if needed, as you're working, you may have to multiply one or both of the half reactions by a coefficient to balance the electrons. Again, as you're balancing these redox reactions, you don't want to lose more electrons than you gain or gain more electrons than you lose, which is not possible. And so we'll look at some examples like that. And then step 6, you add the half reactions back together to get your full balanced redox reaction. Sounds really complex, but with a couple examples under your belt, not going to be too difficult.